Welcome to Fluidic Conversations. My name is Martina. I'm one of the hosts of Fluidic Frontier podcast series, where we host discussions on the state of up-and-coming innovative technologies, so new discoveries, challenges, and future developments. Following each one of our podcasts, we release an issue into our Fluidic Frontiers magazine with our upcoming issue focusing on water in particular. So today we are joined by Dr. Bas Vriens and Dr. Kariyawasam from Queen's University, who have both done some very interesting research on the behavioral of environmental contaminants. So Dr. Vriens has a bachelor in chemical engineering, a master's in earth science, and a PhD in environmental system sciences, with a research focus on behavior of emerging contaminants and the impacts of large-scale waste streams. Dr. Thamali Kariyawasam is a postdoctoral fellow. She has a background in molecular biology and genetics, and a special research focus on the development of a specific type of green algae, which I'm not going to even try to pronounce. So first we will have a presentation from both Dr. Vriens and Dr. Kariyawasam on the research up to date, and this will be followed by a quick Q&A where we will get to uncover more specifics about their work. So thank you again for joining us, and with that being said, I am giving the floor over to you.
Okay, thank you, Martina, for the introduction. Share my screen. And yeah, so as Martina said, we are working with algae, and actually we are trying to use genetically modified algae in wastewater treatment. Essentially, we are trying to generate a 10,000-ton algal liver for the wastewater treatment with a specific focus on pharmaceutical contaminants. So these various different types of pharmaceuticals, which are made by different manufacturers, ended up in surface water in many different ways. And one of the key contributors to this problem is municipal wastewater, which is coming from households and hospitals. This is because the drugs we take, we cannot fully absorb them. So we can only absorb up to 50% of the drugs we take, and the remaining 50% is excreted and ended up in wastewater treatment facilities. And unfortunately, the conventional wastewater treatment facilities cannot fully eliminate these drugs, so that they ended up being in the surface waters and also in the drinking water as well. And there are advanced techniques like ozonation, membrane filtration, like that we can incorporate into wastewater treatment facilities, but they require very high infrastructure upgrades, and they are very costly. So because of that, the pharmaceuticals receive actually widespread attention as contaminants of emerging concern. And this is one example which was posted by CDC early last year. And this was coming from a local environmental committee where they tested waters in Granby, Bromont, and Covensville. And they found that the samples they have taken in 2019 and 2020, the concentration of certain drugs was 75,000 times higher in treated water after treating them. So which means, or confirming that our conventional wastewater treatment facilities are not enough to tackle this problem. And this is another study which came earlier this year, which shows that the surface waters actually contain drugs. These were samples taken from St. Lawrence River and major tributaries. They found that there are high amount of pharmaceuticals like diclofenac, carbamazepine, venlafaxine, and ibuprofen, like pain medications. There are high levels of these compounds in these surface waters as well, which comes to our overarching question about how can we address this growing issue of pharmaceutical contamination? Because we use enormous amount of pharmaceuticals, and then we cannot absorb, like humans cannot fully absorb them, so they ended up being in wastewater treatment plants, but conventional wastewater treatment plants cannot fully decontaminate them, and upgrading them is costly. So we have a big problem. So how can we deal with it? So as I said, the municipal wastewater is the main contributor to this problem. And this is because we cannot fully absorb them. So actually, when we take drugs, they are absorbed by the human liver. And it is done by specific enzymes called cytochrome P450s. They are actually present in human and in other organisms as well. And the human cytochrome P450s are actually mainly involved in degrading drugs. So what we are trying to do right now, actually, how about creating an external liver? Because our liver is not enough to degrade all these drugs, right? So how can we create, or how about creating an external liver by giving this liver function to these tiny organisms called wastewater microalgae? So they are actually readily present in wastewater, and they do not need any nutrients or any additives. So you don't have to upgrade your wastewater treatment facilities. They only require light source so that they can make their own food. So if we can give them the human liver capabilities, and if they can act as tiny livers themselves, they can act as a liver and then finish the unfinished business of the human liver, so that we can have a better solution, like a cheaper option for this pharmaceutical contamination problem. So this is actually what we are trying to do in our project. And to address this issue or to achieve this goal, we had two aims. First is to selectively express cytochrome P450s, which are the genes that are involved in degrading drugs in microalgae, and also to ensure that these genetically modified algae are not freely floating in the environment. So we took how to contain them into a specific place as well. So to achieve the first question or the aim, we actually focused on two different types of cytochrome P450s. One is from human, which have a very wide substrate or like pharmaceutical specificity, so they can degrade very different types of drugs coming from chemotherapy, therapeutics, antipsychotics, antidepressants, so forth. And the other one is coming from a bacteria called Bacillus megaterium, which also has a high range of substrate metabolism activity, which is again chemotherapeutics, antipsychotics, antidepressants, so forth. So essentially, our aim is to introduce these specific genes which have the drug metabolizing activity into the wastewater microalgae. So in that case, we have two different candidates, one from human, one from bacteria. And as our wastewater microalgae, we are using a specific algae called Chlamydomonas reinhardtii, because it's a well-known model organism and they have well-established genetic manipulation method. And as a start, we tried to introduce these bacterial genes into these algae, and then tested whether actually these genetically modified algae can do this drug degrading like properties. So this is some of the results we got. So we started testing these algae with a pesticide called Duron. It's actually a widely used pesticide and also can be observed in surface waters as well. So here what you can see is the WT is wild type, and these are two different genetically modified strains. And if they are green, it means they are healthy and they can grow well. So what you can see right here is when we increase the concentration of this compound, the wild type can survive up to 5 micrograms of the compound, but then these genetically modified algae are very resistant, can survive up to 30 micromolar concentration of Duron, which is good, because when they have these P450, they have better resistance to the compound. And also the most important thing is when they have the BN3, they showed drug degradation up to 50% at day 7, where the wild type is only 7%. So it means they are doing the job that we want them to do. So taking these all into account, so our conclusions are the genetically engineered microalgae, they showed improved resistance to Duron, like we tested with one, compared to the wild type, and also they show the degradation of this compound compared to the wild type. This is good news. So what it means is now, because we observe this trend with one compound, now we can test this genetically modified algae with many different types of pharmaceuticals, many concentrations, many different types of wastewater conditions, and see how well they can tolerate these compounds, how well they can grow, and actually whether they are doing the job they are supposed to do, like whether they can act as livers degrading these compounds. A promising strategy for the wastewater bioremediation, because this is again cheap and also sustainable as well. That is where we are when it comes to aim 1. And in aim 2, so the next one is we don't want to like release these genetically modified algae freely into the environment. So we were thinking of how to contain them in a specific place. So what we were trying to do is we tried to trap them in a specific gel matrix, which we called as algal beads. So once they are trapped, they look like this. They are like boba in your bubble tea, green boba in your bubble tea, and they cannot escape into any place. So we try to see when they are trapped in these beads, they can grow, whether they can grow as they are free, and also whether they can do the biodegradation compared to they are in the free form. So the two aims were actually done concurrently. So when it comes to beads, we use wild type cells. And to let you know, like the wild type algae can also degrade drugs to a certain point. They can absorb the drugs and degrade using their enzymes themselves. So we use wild type algae and tested them with diclofenac. It's another very commonly used drug. And we use again chlamydomonas and also another algae called Senodesmus, and them together as well. And this is the growth in free cells and in the trapped cells. And what we can see from here is the trends are similar. So when they are trapped, they grow well as when they are free. So the trapping doesn't impede their cell growth. And also we tested whether they can degrade same when they are in the trapped form. So this is again free cells, and this is the trapped form on the right. So we can see the similar trend. So when they are in the free form, like they are doing the degradation even better when they are in the trapped form. And when they are together, they do the degradation better than when they are alone. So combining them together, so when all these tells us is in immobilization does not impede the algae growth, and also it can show similar degradation capabilities as they are in the free form. And in the long run, what this tell us is now, because they are working as the same to the free cells when they are in the trap form, now we can use these genetically modified algae in the trap form. We can use different algal combinations, and then we can, based on the wastewater treatment facility, we can use different types of algae and do the treatment when, because they are contained, we can collect them easily after that. And also we can change the bead composition, like not the composition, but the size as well, so that depending on the wastewater treatment facility, we can check these different conditions and find out the perfect match for each wastewater treatment facility as well. So to wrap up, we started, or like the overarching question like we are trying to address is how can we address the growing issue of pharmaceutical contamination, because the conventional wastewater treatment facilities cannot fully eliminate them. And the municipal wastewater is the main contributor to that. We are trying to use or give the human liver function into the wastewater microalgae, which are already present in the wastewater, so that they can finish the unfinished business from the human liver. And for that, we use specific genes called cytochrome P450s, which have the ability to degrade drugs. We started with a gene called BM3 coming from a bacteria and introduced into a wastewater microalgae called chlamydomonas. And we observed when tested with the pesticide called Duron that they are resistant. They show better resistance to higher concentrations of Duron, and also they have increased degradation capabilities. And also we wanted to find out a method to contain them as well, so that these genetically modified organisms are not released into the environment. So we try to trap them into a gel matrix. And when we do our preliminary experiments with wild type, we observe that when they are trapped, it doesn't impede their cell growth or degradation capabilities. So they are all good news. So the next is just to use the genetically modified algae in the trapped form and test different types of drugs and wastewater compounds and see how well they can behave. So kind of the summary of our project. And so this is funded by New Frontiers Research Fund, and it's a collaboration of many different departments of Queens, starting from geological, biomedical to chemical engineering, and yeah, many different people. Yes, that's kind of an introduction to our project. And yeah, we can take questions.
So much, Dr. Kariyawasam. I really, really appreciate you sharing that. I wanted to go right into some questions. It seems like what you guys are doing is very, very innovative and extremely unique, at least from what I've seen. I'd love to ask and hear about what initially drew you to this area of research from both of you, where you came from, your specific backgrounds, and how it drew you to this. What kind of sparked the interest in this particular field?
You want to take that question, Thamali, or should I?
I can tell from my background. So as I said before, so I'm originally from Sri Lanka, and I did my undergrads in Sri Lanka in plant biotechnology. And I started my graduate school at University of British Columbia in algal genetics. And I did my master's and transferred to my PhD. And in that area, like I was looking at mostly the life cycle, one of the life cycle stages of that algae. And after I'm done with my PhD, I found this project which is incorporating the algal biotechnology background I have into a very practical aspect. And I think the pharmaceutical contamination problem is a very huge problem these days. And different people are trying to use different methods to cope with it. And then using genetically modified algae is a very unique area. And actually using these drug metabolizing genes in algae is again like no one has tried that before. So when I see the opportunity, I was really excited to join the project and see how it goes and try to see how much we can achieve. And I think that's how I ended up in here at Queens.
Would you like me to add something to that, Martina, or are you good?
Feel free to add your own, because you have a very interesting background. So I'd love to hear your story as well.
Yeah, this project kind of came about when I was having a chat with the other PI on the project, Dr. Petkovic, and this is the pharmaceutical problem is large. It's happening all over the world, certainly in industrialized countries, and it struck us that for many of these wicked problems, people tackling it tend to come from isolated disciplines. And Martin was discussing, he's from and you as well, Thamali, like a more of a biomolecular background and pharmacology, that a lot of solutions to problems come from tackling the root cause. And so we started thinking about, okay, what is known about these drugs? How are they developed? And how do we test their uptake and think about ways the human body can actually process these medications, until it struck us that maybe this is an opportunity for us to then tackle the other end of the cycle of this problem, where it becomes a problem, and maybe we can leverage that. And so what I think is nice about this project is it involves such a lot of people from different backgrounds, as Thamali alluded to, people from environmental engineering, chemical engineering, that really look at sort of the process side of things. How can we actually implement this technology at scale in practice, versus the people who do the fundamental pharmacological and biomolecular research and the genetic engineering, of course. It really makes it exciting and creates this opportunity where we can learn from each other to come up with a solution, right?
No, exactly. Thank you for elaborating on that. My next question is, well, this is of course very innovative method. So I imagine there has been some challenges in exploring this as a solution to bring into research, right? So what are some of the challenges that you have both personally faced as you have explored this area of research?
I'll let you talk, Thamali, about the
Yeah.
technical challenges because
Mhm.
the actual engineering work, the genetics are quite complex, and there are so many there's so many knobs to turn and so many variables to consider, and we want to make sure that we're as efficient as possible. But there is another hurdle, I think, on a larger scale that we were concerned about, which is, how do we ready this approach for an actual deployment and actually implementing this in practice. And so, as Thamali said, there are all these alternative technologies available, ozonation and chlorination and all kinds of expensive treatment technologies that are available. This would, of course, if successful at scale, be a cheaper version to remove those contaminants. But you can imagine there are quite a lot of concerns from the public about, what would it mean if we start introducing genetically engineered, microorganisms, algae and bacteria to the process? Is that going to affect my drinking water? Is
Yeah.
that going to affect ecosystems? And so one example is that we try to address is the risk of renegade organisms. How do we reduce the risk of those genetically modified organisms to flush out of a treatment facility and affect downstream environments? And so that's where where Thamali came up with this bead process to make the containment a bit more feasible, I guess. So yeah, there are a lot of hurdles and challenges that we think about when it comes to the upscaling. And the next thing that I think this project is headed to is to work with practitioners to try and pilot a selection of these organisms at a larger scale. Of course, our ultimate goal is to work with partners to deploy this in actual facilities, but we're still years away from that. That's the next step for us. Yeah.
Perfect. Thank you. Anything you'd like to add to that, Thamali?
Yeah, I think Bas explained the bigger problems. Like I can tell, like the technical problems, we had so many, like when we express these foreign genes in these tiny organisms, like sometimes they can die from the genes that we express. So we had trouble expressing these genes, and we tried multiple different methods of introducing the foreign genes in the microalgae, and a better method on how to test these. So yeah, I think every step was challenging up to now. So, but we are glad that we could actually have some proof of concept that where we can show that actually this is working, so that we can use this as a platform, and then we can improve on this on top of this. So yeah.
Perfect. So you kind of touched on my next question, but I was going to ask what are the future developments that you're looking at in future projects? Is there something in the field that you are really interested in seeing develop more? Something that maybe doesn't have enough spotlight in your opinion? Or what are you looking at really in the future?
I think what's really exciting about this technology is that theoretically, and I guess technically as well, what you could do, or what this method allows us to do, is to tailor a treatment process to a particular type of wastewater that a facility is having issues with, right? So you can imagine if you have a large urban area, there's a cocktail of pharmaceuticals coming in, and there's evidence to show that a particular compound is problematic, then theoretically we would be able to design a community of microorganisms that has been engineered to tackle particularly that incoming group of pharmaceuticals. So it really allows for a sort of tailoring to the particular conditions, and also to the operational sort of setting that those different types of wastewater treatment facilities have. So that is, I think, a big advantage that we have, and I'd certainly be interested in exploring. I'm not from a molecular or biomolecular background, and so talking to these other project partners has really opened a lot of new ideas in the group, I guess, because there are a lot of problems in the food industry or in aquaculture where we could harvest the capabilities of microorganisms to perform certain tasks, not just cleaning up wastewater, but maybe to make another chemical process more efficient. So there are tons of opportunities to explore, and I think this field is going to see a lot more applications going forward.
I'm glad to hear that. Anything you'd like to add to that, Thamali?
No, I think that's
Okay, perfect. I saw, Dr. Bas Vriens, that you have several different types of projects. You're also involved in mine waste monitoring. I'd love to hear a little bit about that. Anything about their current waste management processes, anything you're looking to develop in that area, or do you have any advice for students that are looking to pursue research projects in that area?
Yeah. So my research on mine waste is also focusing on wastewater to a large extent. Interestingly, the wastewater that comes off of these mining operations is very, very different than your typical municipal wastewater. So we're talking about less nutrients, less organic matter, typically more metals and other salts that are in there. So the treatment techniques that they deploy, in a municipal facility versus in a mining operations, they are very different. But there are some parallels, and there are probably a lot of things we can learn by crossing over between those two fields. A lot of the treatment in the mining context is more sort of chemically focused, and there's a lot of exciting chemical engineering going on. But microbes, we know, play a large role in the weathering of mine waste and play a large role in sort of controlling how mine wastewater, has a certain composition or how much metals it contains. So leveraging the capabilities or the potential capabilities of microbes to do those different types of functions is something that I'm also really excited about. And then kind of working with these people like Thamali, these genetical engineers and biomolecular scientists. I think there's a lot of opportunity to see if we can maybe deploy similar strategies in a mining context. And if students are interested, I would say Google, reach out to people. There are many more professors and scientists in Canada and around the world that are very interested in this field, and there's tons of opportunities. So I encourage everybody to just reach out, start a conversation, and go for it.
Perfect. All right. Well, I'd just like to thank you both for joining us today, and I really appreciate your insight. I think very innovative what you're doing. I will definitely be staying up to date on your future projects and looking to hear about this research some more. So thank you again, and we really appreciate your time.
Thank you.
too.
Thank you for reaching out.
Thank you. Take care. Bye-bye.